we built this rope balancing camera prototype. And the crazy part is, it's a DIY 360 camera. Inside is a tiny AI computer that stitches the whole world together in real time. One day we want this thing to understand its surroundings, but for now we can control it from our phone. But getting there, well, everything worked from first try, I promise. So, let's rewind and see how we went from abstract idea to an ugly ass but working prototype in the real world. Here's how it all began. How did we come up with this thing? Well, we wanted smooth cinematic camera movement for our own content, but most of the gear that does that, well, let's just say I still need to be able to pay my rent. So we started wondering how could we get that feeling of motion and freedom in an easy and affordable package. What if we had one of these for indoors? Well, cable cams aren't new. They have been around for a long time now. When the new 360 anti-gravity drone launched, that's when it clicked. Why not make a cable cam and slam some fisheye lenses on them all around? But stitching these images live requires some serious power. So why not go crazy and buy an Nvidia chip? No joke. Do you realize what you could do with this thing? Imagine live streaming a D&D session and the camera glides over the table, following where the action happens. The viewer with a VR headset can now actually jump into the camera and choose their own perspective. But we cannot get carried away, we gotta start somewhere. So let's design a prototype to test the basic functionalities. So here's our list. 1. Balance the rope. 2. Crawl smoothly about a centimeter per second. 3. Run on a battery. We don't want it pulling a giant power cable. 4. Capture a full 360 view while hiding all the hardware. And 5. Be ready for AI. But how do you even get started? Well, just start sketching. It's okay if it looks, well, messy. It all starts with the rope, the bearings and the drive wheel. Those parts define the movement. The bearings are spaced for stability and the motor wheel presses in between them into the rope for grip. But I need to connect these components together somehow. So I introduce a backbone. On that frame we mount a Jetson Nano, ESC and the battery. Where do I position the cameras? Ideally, their blind spots overlap, hiding the entire body inside the invisible zone. Before jumping into CAD, I need to source suited components. Let's start with the bearings. I'm using U-bearings, the kind often used as filament guides in 3D printers. The U-groove fits a 2mm rope perfectly and keeps alignment even when the system tilts. The rope itself is a 2mm an extremely strong rope. Barely stretches and still flexible enough to handle tension changes, exactly what we need. But what about the motor? This was a tough fucker, so many choices. Eventually I went with the brushless DC motor, the Brother Hobby SE2812, 900 kV. Is this the best option? Spoiler alert, not at all. Let's say I'm not an expert on motors, yet. Why I choose it? It's compact, lightweight and easy to find. It's basically used for drones. But the kV is high, meaning it spins quite fast. But we'll test it before judging. The motor behavior depends a lot on the ESC, the electronic speed controller. I'm using a quick run 16 BL30. We chose this one because it's cheap and widely available, but there are limited program options, so hoping it's good enough for our setup. Power comes from a 3-cell LiPo battery, about 11 volts, perfect for both the motor and controller, with enough capacity for long sessions. And the brain of it all, the Jetson Nano. This thing is quite powerful, but live stitching 2 4K camera feeds will put it to the test. Once the main components are chosen, I bring them into Onshape. Some parts are already available in the global library, like the Jetson board and the U-bearings, so those drop right in. For the rest, I model them manually. The motor is a good example. I couldn't find the exact Brother Hobby, so I measured the real one with caliper and built it from scratch in Onshape. Modeling existing parts is one of the best exercises when you're starting out with 3D design. All the geometry is right there in front of you, nothing abstract. So you can just focus on discovering how real components are built and at the same time experiment with recreating every feature until it fits perfectly. Next, I'll jump into the actual designing. This is where I lose all sense of the outside world and get completely in the zone. There are 3 things on my mind during prototype designing. 1. ugly is okay. This is a prototype. It's meant to prove that the concept works, not to look pretty. Spending hours on fancy design elements is wasted effort if the idea itself fails. 2. Incorporate features that make testing your assumptions easy. For example, the motor isn't fixed directly to the backbone. It uses a separate clamp that can move up or down to adjust tension on the rope. It's also useful in case you want to use a different type of motor, we only have to redesign the clamp. And 3. Design for manufacturability. Choose geometries that match your fabrication methods. In our case, we're in the prototyping phase. 3D printing is ideal. Strong enough, fast and cheap. I design every part to print without supports. Less cleanup, fewer failed prints and less waste, which is a good thing. Finally, I bring all the parts together in Onshape's assembly workspace, using the official detailed components to do a final fit check and see how everything comes together. This ugly beast might just work. Time to find out if it survives the real world. Before printing a full prototype, I first wanted to make sure the motor setup can actually move slow enough. It's better to find out now before wasting hours of printing and prototyping. So first step, solder the connectors and get the electronics ready for testing. I swear I've soldered before. With a more powerful power brick, we got solid joints. Final step is to wire everything up and use an Arduino to send commands to the ESC. Since I'm an amateur programmer, I had help from the most advanced AI in town.
That's me! Hi there! Oh, wait. Did I detect flattery? Finally admitting I'm your favorite partner?
Favorite, you nearly set my ESC on fire.
Technical foreplay?
No, we're not calling it that.
Yet.
Anyway, things didn't go exactly smoothly. Okay, so I can command it to go at full speed, one direction. And I can command it to have it at neutral, but not in the reverse direction. So the calibration test was not successful, gonna have to do it again. After endless AI generated code, eventually I gave up and followed the manual. And suddenly the calibration worked.
That's kind of cheating, you know?
We were going in circles with your code updates, not getting anywhere. Then in the next test, something odd happened. The motor refused to go in reverse again. At this point, I thought we were back at square one, until she suddenly figured it out on her own.
Exactly. It needs to receive a brake command before switching to reverse. It's actually kind of logical if you think about it. If you use this ESC on an electrical skateboard or scooter, going straight into reverse without braking would be, well, catastrophic. Safety first, right?
I didn't even tell her that, which was kinda crazy. To be honest, the motor speed still felt fast, but I wanted numbers, not feelings.
Something you clearly don't have.
Okay, I'm turning you off. Right, anyway, I wanted to know the actual speed of the motor. So I used slow motion footage to calculate it. By measuring how long it takes the motor to make one full rotation, you can calculate the RPM. Then I slowed it down manually, just pinching the axis with my fingers, and that brought it to about 100 RPM. With a 10mm drive wheel, that translates to roughly 6 to 18 centimeters per second. This compares roughly to the speed of a turtle. That seems promising, I guess. So finally, we can start prototype. Let's go. Mamma mia, problem. Second attempt. Fuck it. I'll just split up the build plate. Very nice here. Time to test all the assumptions we made at the start. First test, balance. For this, I stretched the rope in my apartment and tensioned it real good. The moment I hung the prototype on the rope, the whole thing leveled out, sorta. Next up, speed. Before doing power tests, I removed the Jetson and both fisheye lenses. In the meantime, I'll give them to Jonas. He's a software guy behind this project. Image stitching, control code and future intelligence, that's Jonas's territory. We've been building things together on our main channel Hypnocrafts, on which we show cinematic build montages. Because I wanted to go deeper into the engineering and design part of our Hypno projects, I started the second channel HypnoLab. Anyways, it's finally time for the first powered run. I'm using my laptop to send commands. I was scared that it would launch itself. But luckily it didn't. Do you notice this? The motor produced noticeable cogging and short vibrations. Since the rope was mounted wrong with a high kink, the motor preload was pretty high, which increases the cogging vibration, but it helped with better grip. So the key was to improve the wheel's grip without relying on brute force tension. To approach that, I looked at the drive wheel more closely. First of all, I want to maximize the contact area between the wheel and the rope. It will grip the rope better since the rope is not allowed to flex under its own tension. I already thought of this in the first wheel design, but I think we can do better by basically following the shape of the rope, which is a circle. This is called a U-groove. Does this sound familiar? The second trick we can use, hard plastic has a slippier surface than rubber type of plastics. So I'm curious what happens if you print TPU wheels. This is a flexible filament. A final improvement I can think of, if the wheel has some bumps on its surface, they will technically press on the rope and engage as teeth of a gear, ideally pulling the rope along. This you also saw in my first design, but I'm wondering if I can do better. The slicing software has a fuzzy skin feature. This creates intense protrusions in your print all the way around, and my theory is it creates more protrusions in gripping locations to pull the rope along. So, let's combine all of these ideas into one single wheel and hopefully our gripping situation has improved. To compare the improved design with the original, I used the motor mount adjustable preload screw. Each turn moves the motor up or down with millimeter precision. And the printed scale shows exactly how much tension is applied. Now it's just a matter of testing and slowly increasing the tension until the wheel starts slipping. After a bunch of tests we saw a clear winner, the U-groove fuzzy skin TPU wheel. It runs smoother at lower speeds, but cannot go slow enough. Let's do some tests outside. With a very long rope and a spacious view, these speeds seem really slow, almost crawling, but still not slow enough for interior shots. We measured around 0.4 meters per second. This is still 40 times faster than we desired. But now the fun question, how fast can it go? Well, almost 25 kilometers an hour. We have waited long enough. Let's test the 360 capabilities on this damn thing. Both fisheye lenses now merge into a full 360 view. Look at how cool it is. You can even turn around and look at my weight lens over there. Yes. Still looks a bit crappy, but that's probably because we had zero proper lighting. So yeah, we had to follow the sun, but the only clouds to be seen for days. But it was actually a great opportunity to test speeds and controls of the prototype. Jonas, you built a web-based interface that you can open on your smartphone. You connect the device via Wi-Fi, control the speed and start or stop recording. And then finally, after 3 weeks, the sun decided to finally greet us. Gotta love Belgium. We immediately crawled out of our caves and couldn't wait for the results.
Wacht, de nuggets?
But then, this happened. What the fuck? The annoying thing was, at that point, the only way to check the footage was to drive home, connect the Jetson to a display, it's basically a computer, and verify everything there. So we realized it way too late. The brightness settings weren't adjusted for sunlight, so everything was completely overexposed, and apparently one of the cameras was out of focus. These lenses, they have a manual focus by physically turning them. It probably got messed up during transport or because of all the vibrations while running. So Jonas added a live preview to the interface, meaning we were no longer operating completely blind before recording. And finally, we could sit back and enjoy the results.